This research paper proposes a deep latent state space generative model to capture the interactions among different types of correlated clinical events, such as kidney failure and mortality. The model explicitly models the temporal dynamics of patients' latent states, enabling the estimation of survival distributions with significantly improved accuracy. The authors develop a new discrete-time formulation of the hazard rate function, which provides flexible fitting of general time-to-event distributions without restricted parametric assumptions. The paper highlights the importance of capturing interdependencies among multiple types of clinically critical events in healthcare, as they are often related to or even caused by one another. Existing work on time-to-event predictions has been limited to modeling a single type of event, overlooking the correlations among multiple event types. The proposed deep state space generative model leverages electronic medical records, EMR, time series data to jointly predict mortality risk and capture organ failure risk trajectories. The model is able to simultaneously forecast multiple clinical events and identify their temporal correlations, providing clinicians with a full picture of a patient's medical condition. The authors contribute to the technical significance of the field by presenting a deep state space generative model that captures the interactions among observations, interventions, critical event occurrences, latent patient states, and their uncertainty. The clinical value of this work lies in its ability to jointly forecast multiple clinical events and identify their temporal correlations, supporting clinicians with decision-making. The paper reviews related studies in literature, including clinical predictions, time-to-event predictions, and deep state space models. The author's work combines a deep state space model with a discrete time hazard model, supporting more flexible distribution models and providing better interpretations of the influence among events. In the correlated time-to-event prediction section, the authors describe their usage scenario and problem setting, providing a formal definition of their learning task. They utilize EMR time series data to predict the time of future critical medical events, estimating the distribution of time duration between the time of prediction and event occurrence, as well as the risk of experiencing events of interest at any given time. In the proposed deep state space model, a time-calibrated multiple event risk trajectory is generated, capturing the risk of different clinical outcomes over time. This model integrates patient physiological states, observations, and interventions, allowing for predictions of time-to-event distributions for various clinical events. The model uses a Gaussian state space model with a discrete time hazard rate function, which is dependent on the dynamic latent patient physiological state at each time step. The learning objective and associated variational lower bound are presented to support the time-to-event prediction task. The log likelihood of an event is calculated based on whether the event is observed or censored, with the use of a variational inference method to approximate the posterior distribution of the latent patient physiological state. The evidence lower bound, ELBO, of the log event time likelihood is derived, providing a comprehensive framework for estimating time-to-event distributions in the context of ICU patient care. The proposed deep state space model, DSSM, is designed to predict time-to-event outcomes in temporal event data. The model's loss function consists of two components: the log likelihood loss for time-to-event prediction and the regularization loss, which measures the difference between the encoder and the prior distribution of the latent state. The loss function can be factorized along time, allowing for efficient computation. The model architecture consists of an encoder network, a state transition module, and a hazard rate emission module. The encoder network is a bidirectional LSTM that infers the latent state from the input data. The state transition module is composed of two multilayer perceptrons, MLPs, that model the state transition with and without external influence. The hazard rate emission module is also an MLP that estimates the hazard rate for each event type. The model is trained using a stochastic gradient descent algorithm, and the gradients are averaged across many batches of the training set. The model is implemented in TensorFlow and will be open-sourced. The DSSM is evaluated on the Medical Information Mart for Intensive Care, MIMIC, dataset, which contains information on patients admitted to critical care units. The dataset is pre-processed to include 96 lab measurements and vital signs as observation features, and 8 types of vasopressors and antibiotics as intervention features. The model is trained to predict the risk of in-hospital death and 4 types of organ failures. The model's performance is evaluated using the Syndex, OCROC, and AP metrics. The results show that the DSSM has better predictive performance for time-to-event prediction and is able to uncover meaningful insights about the latent correlation among different types of events. The dataset is characterized by a large number of missing values, which are handled using a simple imputation method for lab measurements and vital signs. For interventions, a more complex method is used to differentiate between missing values that indicate no action and those that indicate a continuous action. The model's performance is evaluated within two fixed prediction windows, 0, 24-hour and 0, 48-hour. The results show that the DSSM has good discriminative power and is able to accurately predict the risk of events within these windows. The paper presents a novel approach to predicting patient mortality and organ failure in the intensive care unit using a deep state space model. This model is capable of encoding temporal correlations among observations, interventions, and hidden states, which are then rolled out to the prediction horizon step by step to generate the hazard rate for each event. The model's performance is evaluated against two state-of-the-art methods, DeepSurv and DRSA, and it significantly outperforms both in terms of AUCROC and AP, particularly in short-term predictions. The model's ability to predict hazard rate trajectories is demonstrated through Figure 5, where observed and censored events are plotted. The fitted hazard rate accurately captures the true event time for both observed and censored events, with the hazard rate being significantly higher for observed events than censored ones. Moreover, the model reveals correlations between mortality and organ failures, as shown in Figure 6. The hazard rate trajectories of mortality and organ failures are highly correlated, with varying levels of correlation observed across different patients and organs. This is quantified in Table 2, where mortality is found to be highly correlated with kidney and liver failures in Case 1, and with liver, kidney, and coagulation failures in Case 2. In contrast, in Case 3, mortality is less influenced by neural system and coagulation failures, despite these being predicted with high risks. The proposed deep state space model provides valuable insights into the progression of patient conditions, supporting clinicians with better decision-making. The model's performance, as demonstrated in Table 3, suggests that it can be a powerful tool for healthcare providers in the ICU. This research proposes a deep latent state space generative model to capture the relationships between patients' mortality risk and associated organ failure risks. The model is designed to fit general discrete-time survival distribution of observed events. The authors demonstrate the effectiveness of their approach through extensive experiments on the MIMIC dataset, outperforming several state-of-the-art baselines in terms of prediction accuracy. The model provides meaningful insights into the temporal relations among multiple types of events, demonstrating correlations between different organ failures and mortality risk. The results are presented in Table 3, which shows the time-to-mortality prediction performance of the proposed model, DeepSurv, and two baseline models, DRSA and DSSM. The proposed model achieves higher Syndex and AUC at 2.4, AUC at 4.8, AP at 2.4, and AP at 4.8 values across various organ failure types, indicating better predictive performance. The authors also provide a comprehensive review of related work in survival analysis, listing 36 references that have contributed to the development of their approach. They describe their model as a deep latent state space generative model that captures the relationships between patients' mortality risk and associated organ failure risks. In the supplementary materials, the authors provide details on data preprocessing, including code harmonization, unit conversion, outlier removal, and value normalization. They also list the features and their units used in the experiment, including access pressure, albumin, ALT, anion gap, AP, arterial base excess, and other measurements. Overall, the proposed model demonstrates promising results in predicting mortality risk and associated organ failure risks, providing a valuable tool for physicians to make informed decisions. The authors' contributions include the development of a novel deep latent state space generative model and the provision of comprehensive experimental results and supplementary materials. The proposed framework incorporates a comprehensive set of features to capture the complexities of mechanical ventilation in critically ill patients. Table 6 presents the intervention features and their corresponding units, which include various mechanical ventilation settings and parameters. Specifically, the features comprise dialysate rate, milliliter per hour, fraction of inspired oxygen, FiO2, %, positive end expiratory pressure, PEEP, CmH2O, peak inspiratory pressure, PIP, CmH2O, respiratory rate setting, breaths per minute, BPM, and tidal volume setting, ml per breath. These features are crucial in understanding the mechanical ventilation management strategies employed in the intensive care unit, ICU. The inclusion of these features enables the development of a robust predictive model that can accurately forecast patient outcomes, such as mortality and ventilation duration. The feature set is further augmented by the incorporation of patient-specific characteristics, including demographic information, comorbidities, and laboratory results. The framework's predictive model is based on a combination of machine learning algorithms and statistical techniques, which are designed to handle the complexities of the data. The model's performance is evaluated using a range of metrics, including area under the receiver operating characteristic curve, AUROC, area under the precision recall curve, AUPRC, and mean squared error, MSE. The results demonstrate the model's ability to accurately predict patient outcomes, with AUROC values exceeding 0.9 for mortality prediction. The framework's predictive capabilities have significant implications for clinical decision-making in the ICU. By providing accurate predictions of patient outcomes, the model can inform the development of personalized treatment strategies, ultimately leading to improved patient care and outcomes. The framework's limitations include the reliance on high-quality data and the need for further validation in diverse patient populations. Future work will focus on addressing these limitations and exploring the application of the framework in other critical care settings.